Hello, so in this video we're going to look at introducing something called integration. Okay, so last time we looked at differentiation. So as an example, let's say we want to differentiate x to the power of 3, say, right? Well then that would be well, basically the power comes to the front, right? So it'd be 3x, and then we knock one off, or in other words, subtract one from the power, so it would be squared, right? So that would be the differentiation, the derivative of x cubed, right? But actually, I guess then let's decompose more in a step-by-step, more fundamental way what we're doing, right? So we start with x cubed, and then if we want to explain thoroughly step by step what we did there, well, what's the first thing we did? Well, we brought the power to the front, right? So then the 3 will be in front, so that's equivalent to multiplying x cubed by 3, or in other words, multiply x cubed by the power. Then what did we do after? So we got 3x, then we knocked 1 off the power, we subtracted by 1. So subtract the power by 1, right? And then we're left with 3x squared, right? That's effectively what we did, step by step, broken down, right? That's effectively what we're doing, and this whole process at the end is the differentiation, right? The whole process of what I'm describing here is differentiation, okay? Right, so let me get rid of this this top bit here now. So again, overall, these two steps are how we differentiate something, right? That we've seen before, okay? This is differentiation, right? Okay, so then the question is, actually, we can go backwards, can't we? We can kind of undo the step and go in reverse, right? We're kind of doing the inverse, right? So instead now we start with 3x squared. Then we want to go back to x cubed by going the other direction, right? So we start with 3x cubed, then we go back, we have to do the opposite to each step here. So instead of subtracting the power by 1, we're then going to add the power by 1. Then what we're going to do, we're going to multiply x cubed by the power. Nope, now we're going to divide x cubed by the power. Well, actually, we don't have x cubed, we have 3x squared. So we're going to divide 3x squared by the power, as that's our input, right? By the power. And then we're left with, well, hopefully, we get x cubed back. Let's verify. So in this case, in this direction, right, backwards, we're starting with 3x squared now. If we then go in the left direction, the opposite way, firstly, as we saw, we need to add 1 to the power. So if we add 1 to the power, so that'd be 2, which is the power, add 1, that'd be 3x cubed. Then the next step after that is divide this expression by the power. And actually, we don't have 3x squared anymore, we have 3x cubed, okay? So what I'm going to say is just divide by the power, right? Very simply, and multiply by the power. So dividing by the power then, this power we've got now, well, basically we're going to have 3x cubed is then going to be all divided by the power 3, right? But then actually, if we do, we can simplify this fraction, because 3 over 3 is just 1. So we just get x cubed. Well, what do you know? That's what we started with. And that's what we want. That's what we wanted. That's what we wanted to end up in. So this is actually the opposite process, right? This process here is the opposite to differentiation, right? Hopefully you can see that. It's the inverse, right? You can think of it like function machines, right? So we can go the other way, and if we start with if we start here instead, we end here, so it's the opposite. So this process then, well, the process to the right, that's differentiation. What about the process the opposite way? And you probably guess it. It's called integration. Okay. And so, in general, integration is the opposite to differentiation, right? Or we could say the inverse. Okay, opposite or inverse is up to you, but it's the opposite to differentiation. And actually this result is called the fundamental theorem. So remember when we looked at proof in chapter 7, a theorem is a mathematical statement that is proven to be true. So we know it's true. It's a theorem of calculus. Okay, so this theorem, which is a lot more theoretical because it's been proven in higher level maths. If you go to uni, you'll see it in more detail. But the result from this theorem is actually this process integration is the opposite of differentiation. Okay, as we can see here, and that's what we have here. So so this result is the fundamental theorem of calculus, which you may see thrown around. That's all it means. The fundamental theorem of calculus means that this integration process is opposite to differentiation. Okay, and also calculus. You might be thinking, what that means. Calculus is the study of both differentiation and integration. Okay, so if you see in certain questions use calculus to find that means you need to use differentiation and or integration. Okay, these two topics are combined together to give me calculus. Okay, so if we go back to this diagram now, obviously we've seen that for this particular example we have x cubed, that what the process is, but actually this holds in the exact same way for any power of x. If we switch it to n, if we switch it to n instead of a cubed, it would be the exact same sort of flow chart, right? The same sort of set of instructions. So if we have a look then, differentiation, we multiply by the power, then we subtract 1 from the power, and then integration is this: we add 1 to the power, then divide by the power. That's what integration is going to be. So if we want to integrate, let's say x to the power of n. So obviously last chapter we differentiated powers of x, for example x cubed. But now we want to integrate powers instead. So we want to go the other way. If we want to integrate x to the n, well, we're going to follow the flowchart. What's the flowchart telling me? If we start with this, which again is just another power of x, that would be x to the n, where obviously we have x squared, right? Obviously a number in the front doesn't matter, but we can again follow this sort of set of instructions. So firstly we add 1 to the power. That's what we're going to do first when we integrate. So to integrate x to the power of n, we add 1 to the power. Then what's the next step? Oh, we divide the expression by the power, right? So then divide by the power. Okay, and so we can do that more mathematically then. So integration, the integration of x to the n is going to be, if we add 1 to the power, well, firstly n is going to be x to the n plus 1, right? If we add 1 to the power, then as we saw, then we divide the expression by the power. What's the power now? N plus 1. So we're going to divide f of it by n plus 1. And that is the mathematical way of integrating a power of x, okay? Now, again, there's a lot, very theoretical at the moment, so we're going to look at some examples now. Really, we're going to be looking at this, we're going to just be using this expression all throughout this chapter. In year 2, we'll look at integration of different types of functions of x that are not just powers, right? But for now, in this chapter, the only thing you need to integrate is this. So this rule here is going to be very crucial. But we're going to look at using that now, okay? So, in this example, we are told to find y for the following. dy dx is equal to x to the 4. Well, hang on. So last chapter we looked at saying y, for example, is x cubed. Then we looked at differentiating, right? To get dy dx is 3x squared, for example, right? But this time we're going the opposite way. And this time we're given the gradient, the derivative, and it's asking for y. So we need to go the other way. So we're going to need to integrate, right? Because it's the opposite of differentiation to get to the original function for y. So if we want to go from the derivative, so dy dx, if we want to go from the derivative to the just y, right, the normal function, we need to integrate, which means we will be using this sort of rule we just talked about here. Okay, so y then, okay, so we're going to integrate, which means we have x to the 4. What's our first step, right? If we look at this worded description, if it helps, well, firstly we add 1 to the power. That's what we're going to do. So we're going to add 1 to the power. So instead of 4, it'd be 4 plus 1. That'll be 5, right? Then what's the next step? We divide by the power, so everything is then divided by this power 5. So then we could say y is a 5th x cubed, right? Okay, but there's something missing here. So yes, so let's have a look at this. I'm going to talk about what we just looked at. Actually, no, let's look at what we just saw. So what we just saw, let me get rid of this example and put in the example we've just got, right? So what we've got is dy dx is equal to x to the 4, right? So then we integrated to get back to y. And y, as we just saw, is a 5th x cubed, right? So that means if we were to go backwards from y, if we differentiated y using differentiation as a check, well, firstly we times by the power. So a 5th times 5 is just 1. So we get x, then knock 1 off the power, we get 4. That's great news. That checks our answer should be right. So we can check our answer by differentiating back. But the problem here is, so differentiate. The problem here is, let me pose this. What if instead of just what we just discussed is, if we get our original function for y, if we differentiate, we should get back to this, right? That's what we're doing. But let me pose this. What if I add a number 2 or number 1, for instance? What if we add a number on? Let's differentiate this then. So if we differentiate, well, a 5th x to the 5 is just x to the 4. That's great news, right? That makes sense. That's what we've got. That's what we were given. But then what does 1 differentiate to? You should know any number goes to 0 after differentiation. So we still just get x to the 4. Well, hang on a minute. How come there's a different expression for y? How come this is fine if I just have x to the 5, a 5th x to the 5, but it also is fine if I add 1? What about if I add, say, 2? If I differentiate, that will go to 0. So if I add 1,000, well, that goes to 0 after differentiation, and I just get left x to the 4. if I add any number, even a million over 7 to 8, that's a number that differentiates to 0, and that just leaves me with x to the 4, right? We've got a bit of a problem now, because it's not just this, a fifth x to the 5, right? We've got this situation where we don't have one actual precise answer, because we can just add a number on, and then we still differentiate to get back to our answer, right? So what do? Well, what we need to consider is we need to add something on. So we need to add a plus c, okay? This c is what we call a constant, or a constant of integration, okay? Which means whenever we integrate something, we always need to consider adding a number on, adding a constant on, because this constant will go away to 0, as we've just seen, because c is just a number, right? It's just a number that goes to 0 after we differentiate. We saw that in the differentiation chapter. So that means if I differentiate this y, no matter what value I add on, I always get my derivative to be x to the 4, which is what we're given. So that satisfies what we're given, so it'd still be a correct answer. So that means when we're finding y, by integrating, if we integrate the derivative to get y, we need to add on a plus c at the end of our answer, okay? So yeah, okay, so let's have a look at part B then, right? So part B, we now have dy dx is x to the minus 5. So again, we've got the derivative. If we want to go back to y, instead of differentiating, we're going to need to integrate, right? So we're going to need to integrate this expression here, which means, firstly, we need to add 1 to the power. So we have x to the minus 5, while minus 5 add 1 is minus 4. Then we divide by the power, right? So that would be then divided by this power minus 4. And then we could say that y is minus a fourth or a quarter of x to the minus 4. Okay, you can check your answer by differentiating to get back to dy dx. And so that would be minus 4 times minus a quarter, that would be plus 1. X, then we knock 1 off the power. So minus 4 take away 1 is minus 5. Well, what do you know? That is the derivative, so we know what we've done is right. But again, the problem is we need to add on a plus c, because this c, if we differentiate back, will go to 0. So we need to account for that, okay? So that is my final answer. Okay, I don't know what this number is. I'm going to need more information, but for now, that I'd have to just account for the fact there's a number. Okay, there's an extra number possible for my function for y here. Okay, so that's the process, right? We add 1 to the power, then divide. Okay, then we add the plus c at the end. Okay, let's have a look at some more questions. So we've got f dash of x, which is the derivative function, is 3x to the half. So again, we want to find f of x, so we're going to need to integrate, right? So we need to do the reverse of differentiation. So what we're going to do, well, firstly, leave the 3 where it is, then x to the half. Well, a half, well, remember, we need to add 1 to the power, firstly. So half add 1 is 3 over 2, right? Then we divide by the new power, right? So that'd be divided by 3 over 2, okay? Now, this might look like an ugly fraction, but you can think of it as really 3x to the 3 over 2, all divided by the fraction 3 over 2, right? And then really what you're doing is 3 divided by 3 over 2 to get 2. So that'd be left with 2x to the 3 over 2 as my answer for f of x. But we need a plus c, because again, if you think back to, if we were to differentiate this back to here, a number at the end will go to 0, so we need to account for that. Okay, so yeah, cool. Right, okay, that's part A. Then part B, we have f dash of x now equal to just 3. Okay, so then f of x, well, we're going to need to integrate, right? Well, hang on, there's no x here. There's no x. Well, remember what we can do is we can add on x to the power of 0, because anything to the power of 0 is just 1. So that's fine. Now, if we were to integrate this, well, 3, then x to the 0, we integrate the x part. Well, x to the 0, we add 1 to the power first, so that'd be x to the 1. Then we divide by the power, so we're dividing by 1. Well, that's just itself, so it's 3x, and then to the power of 1 is just x. So we just get 3x, okay? And we need to add on a plus c at the end there. And so, yeah. Cool. Okay, we got this question now. We got dy dx is 6x, add 2x to the minus 3, minus 3x to the half. We need to find y. So we've got the derivative again. We need to find y. And again, we're going to integrate as a result to the other way. So instead of differentiating y to get the derivative, we need to integrate the derivative to get back to y. Right, so again, like with differentiation, we could integrate each power of x individually, okay? So we can do this as like 3 different integrations, okay? So firstly, to integrate 6x, well, we have 6x, then x has a hidden power of 1, right? So we add 1 to the power, 1 add 1 is 2. Then we divide by the power, which is then all over 2. Then we integrate this expression here. So 2x to the minus 3. Well, we have 2. Again, just a number. The number in the front doesn't matter. All we care about is integrating the x part, right? So then the x part, well, x minus 3 for the power. We add 1, so it's minus 2. And then we divide by that power of minus 2. Then lastly, we have minus 3x. Then we integrate the x part. So a half, the power add 1. A half add 1 is 3 over 2. Then we divide by 3 over 2. Okay. And then we can just simplify these fractions, right? Well, 6 over 2 is just 3. So 3x squared. Then 2 over minus 2 is just minus x to the minus 2. Then this last part here, this is minus 3 divided by 3 over 2. Okay, it might be handy to put that in the calculator. A bit unsure. But minus 3 divided by 3 over 2 is minus 2. So minus 2 x to the 3 over 2. And then we need a plus c at the end. Always forget your always add your plus c. Do not forget that, because that will then differentiate if we were to go the other way to get my original expression here, because that go to 0. Okay. Right, cool. There we are. So hopefully you're starting to get a sort of idea now. The idea is we add 1 to the power and then divide by it, right? Okay, so we've got some more examples then. So we got f dash of x equal to these expressions here. And again, we need to find the original function f of x. So firstly, f dash of x in part A is 12x. Add 3 over 2 x to the minus 3 over 2. Add 5. So, if we want to integrate them, when we integrate each part of each term of x separately, well, 12x firstly, 12x, we add 1 to the power, so at power of 1, 1 add 1 is 2. Then we divide by the power, so 2. Then we have 3 over 2, x, then minus 3 over 2, the power, we add 1. Minus 3 over 2 add 1 is minus a half. Then we divide by the power, minus a half. Then we have 5. Right, now 5 again is just, we can write it in terms of x because it's x to the 0. Then we add 1 to the power, so 5x to the 1 all over 1. Okay, then okay, so then we just simplify the fractions. Well, 12 over 2 is 6x squared. Then this monstrosity here, again, you can think of it as the fraction 3 over 2 divided by the fraction minus a half. So 3 over 2 divided by minus a half gets me minus 3. So minus 3 x to the minus a half. And I'll note that down actually. What I did there was 3 over 2 divided by minus a half. And that gets me minus 3. Okay. And then lots of x to the minus a half. So that's what I'm doing there. Okay. You'll probably see some ugly fractions here. But just divide the top fraction by the bottom one. Okay. Right. Then we have 5x over 1. That's just 5x. And lastly, what do we need? A plus c. Cool. So again, whenever you integrate, you need to add a plus c. Part B. We now have f dash of x to be equal to 6x to the 5, add 6x to the minus 7, add minus 6x to the minus 7 over 6. Right, okay. So we want to integrate from the original function, from the gradient, from the derivative. So again, we're going to integrate the x's separately. So firstly this, well, 6x to the 5, 6x. Then 5, we add 1 to the power to get 6. Then we divide by the power. So then we divide by 6. Then we add 6x. Then we add 1 to the power. So minus 7 add 1 is minus 6. Then we divide by that. So minus 6. Then we have minus of 6x. Then minus 7 over 6. If we add 1 to the power, so minus 7 over 6 add 1 is minus 1/6. Okay. Then we divide by the power, so minus a 6. And then we can just simplify the fractions. So we have 6 over 6, which is 1. So x to the 6. Then we have 6 over minus 6. That's negative x to the minus 6. Then lastly this, well, this is basically minus 1/6 divided by minus 1/6. That's just 1. Okay, so we get left with add x to the minus a 6. Right, because what I did there was the fraction on top is minus a 6. Then I divided by the fraction on the bottom of minus a 6. Well, that just goes to 1. Okay, and that's how I got to that answer. And we need the plus c. Okay, cool. Part C, we have this expression. So f dash of x is a half x to the minus a half minus a half x to the minus 3 over 2. So again, we integrate to get the original function back. So f of x is going to be, well, a half x. Then we add 1 to the power. Well, minus a half add 1 is plus a half. Then we divide by the power. So divide by half. Then for the second part, the second term here, minus a half x. Then minus 3 over 2. If we add 1 to the power, it will be minus 1 over 2. Then we divide by that power of minus a half. Okay, then we just simplify the fractions. Well, hopefully you notice a half. These fractions on the top and bottom are the same, so they effectively cancel, so I get x to the half. Or, to be extra safe, just put it in the calculator, you should get 1x to the half. Then, it's the same story here, minus a half just gets me plus x to the minus a half. And that is my answer, with a plus c at the end. And there we are. Cool. Right. So hopefully you start to get a sort of grasp now about how we integrate expressions by adding 1 to the power and then dividing by it. Then we have this final question here. So we have that dy dx is equal to 2x plus 3 squared, and we want to find y. So we want to find the original function. We're going to integrate. Well, what's the problem here? Likewise with differentiation, we need to make sure the x's are in suitable powers, so it resembles x to the n. The problem is it's all in these brackets and we can't integrate with the whole bracket thing. We need to expand it, right? So before we do any integration, we need to expand it to get just powers of x, right? So if we expand this, well, that's the same as 2x plus 3 times by itself. Then we just expand this bracket, which will get me 2x times 2x is 4x squared. Then 2x times 3 is 6x. And then 3 times 2x is another 6x. 3 times 3 is 9. Then I can clean this up to get 4x squared, add 12x, add 9. Now I can integrate this, right? Therefore, y, if I integrate 4x squared, well, 4x, we add 1 to the power, so we get 3, divided by the power 3. Then for 12x, it's 12x has a power 1, 1 added 1 is 2, then we divide by 2. Then 9, again, well, at this point, hopefully you can start to recognise that really, 9x, it will just go to 9x, really, okay? If you have a constant, it will just add on an x at the end, effectively, okay? So, then I just need to clean up the fractions, if I can. Well, 4/3, so that's 4/3 x cubed. Then we have 12 over 2, that's just 6 x squared, and plus 9x. And then we need a plus c on the end. And there we are. That is my expression for y. So that's it, right? So, yes, so really the two main results we've used in this section is this idea about integrating by adding 1 to the power, then dividing by the power, and also using the fact that integration is the reverse or the opposite of differentiation, which means if we got the derivative, we can go back to finding the original function by integrating. So instead of differentiating from the gradient, if we had the gradient, then we need to integrate to get back to the original function. Okay, these two ideas are very important. We'll be using throughout the course. But yes, so hopefully you start to get the idea basically of how to integrate powers of x. Now, cool, so I'll leave it there. I'll see you next time.